Hi, this is Mrs. Basin. Today we're going to talk about applications of the equilibrium constants, which is section 15.5. So what we've talked about so far is what K means. So what K tells us, or how large K is, indicates which direction the equilibrium lies. So like we said before, if K is very large, that means that the reaction tends to proceed to the right, where it's very product favored. If K is a lot less than 1, then the equilibrium mixture contains mainly reactants, or like we say, it lies to the left. The other thing we can do is once we know the equilibrium constant, we can compare the equilibrium constant taken from equilibrium values to a constant called the reaction quotient taken when it is not at equilibrium, and it can help us predict the direction in which a reaction will proceed to achieve equilibrium. So this is called the reaction quotient, which is Q, and what you do with Q is you substitute the initial concentrations of reactants and products into the equilibrium expression. So Q is set up the same way that K is set up, except Q is calculated when you have values that are not at equilibrium, whereas K, you use values that are at equilibrium. So it gives you the same ratio, but it's for a system that is not at equilibrium. So when you set up a reaction quotient, like I said, you do this just like you set up a K. So you take products over reactants and you raise them to the power of the coefficient. The difference here, though, is that when you calculate a Q is for concentrations at any time. K, you can only calculate when you have the equilibrium concentrations. So once you have a Q value and a K value, you can compare the two and make some generalizations about what's going on with that reaction. So if Q is equal to K, then the system's at equilibrium. So if those two values are equal, then it's reached equilibrium. If Q is greater than K, then the reaction will proceed to the left to reach equilibrium. So if Q is more than K, then the equilibrium is going to shift to the left in order to reach equilibrium. If Q is less than K, then the reaction will proceed to the right to reach equilibrium. The other application that we're going to look at, and we did an example of this yesterday, is looking at calculating equilibrium concentrations if you're not given any values of equilibrium. So to do these, you use X as the change in equilibrium, and then you sometimes have to do the quadratic when you're actually calculating the values for equilibrium. So for this particular type of problem, instead of being given the initial concentrations and at least one equilibrium concentration, these particular problems, you'll be given a K value, and then you'll have to use an X to represent the change. So we'll go over an example of that one too. Okay, so this first example is a K versus Q problem. So what we're going to do first is it says at 448 degrees Celsius, the equilibrium constant is 51. So we want to predict how the reaction will proceed to reach equilibrium at that same temperature if we start with 2 times 10 to the negative second moles of HI, 3 times 10 to the negative second moles of I2, and 1 times 10 to the negative second moles of H2 in a 2-liter container. So, like we said yesterday, if it is not in a 1-liter container, then you need to do a calculation to get that concentration where you're taking the moles divided by the liters. So when I set this up into the Q, I'll go ahead and do that. So when we set up the Q, just like we said before, it is just like K, except the values are not at equilibrium. So I still take products over reactants, and I'm raising them to the power of the coefficients. So that's my Q expression. Now I'm going to sub those values in. So for HI, I have 2 times 10 to the negative second in 2 liters, so that is 0.01, and I'm squaring it because of this. And then for H2, I have 1 times 10 to the negative 2 divided by 2, so that's 0.005. And then 3 times 10 to the negative 2 divided by 2 is 0.015. So then when I calculate that, I get 1.3. So my Q value is 1.3. And just like K's, Q's do not have units either. Okay, so it told me up here that my K value is 51. So Q is 1.3, K is 51. So in this case, Q is less than K. So that means the reaction will go from left to right. So since Q is less than K, it will proceed in the forward direction to reach equilibrium. Okay, here's another Q example. It's a little bit easier because these are all given in concentration, so we don't have to do any concentration calculations first. So my reaction is given up here. So I'm going to set up my Q. So Q is SO2 to the second, O2 divided by SO3 to the second. So then when I substitute those values in, I have 5 times 10 to the negative third squared times O2, which is 3 times 10 to the negative 2, divided by 2 times 10 to the negative 3, also squared. So this Q value ends up being 0.2. It tells me up here that my K value is 4.08 times 10 to the negative 3. So now, in this case, Q is greater than K, so that means the reaction will go from right to left. Okay, so it will go in the opposite direction of the last one. So it will go from right to left. It will form reactants to reach equilibrium. Talked about in class is what if they give you the K value and some of the equilibrium values, but not all of them. So this one you're just basically substituting these in and solving for what you're missing. So for this reaction, we have the Haber process for the synthesis of ammonia. So the equation is given there. So when I set up my Kp, and I'm going to use pressures for this one just because these are all gases, I have the pressure of NH3 squared over the pressure of N2 times the pressure of H2 raised to the third. And again, those come from the coefficients. So this should have a 3 up here because it wasn't balanced the way it was given. So this is my K expression. So what they have given me is they gave me the Kp, so I'm going to sub that in, 1.45 times 10 to the negative fifth. And then for the equilibrium mixture, they tell me that H2 is 0.928, N2 is 0.432. I'm looking for NH3. So this top one I don't know, but they give me the two bottom ones. So 0.432 and 0.928 cubed. So if I rearrange that and solve for the pressure of NH3, don't forget to take the square root of it because it's squared, I end up with 2.24 times 10 to the negative third, and the unit for this one is ATM because we're solving for a pressure. So this is not the K, this is a final pressure.